Many chemical compounds, such as carbon dioxide, methane, water vapour and nitrous oxide, occur naturally in the atmosphere and have an important role to play in the natural physical process called the greenhouse effect. This process regulates Earth's temperature, keeping it at optimum levels needed for life to exist. Without the greenhouse effect, the world's average temperature would be minus 18 degrees Celsius. These greenhouse gases allow direct sunlight, that is, relative shortwave energy, to reach the Earth's surface unimpeded. As the shortwave energy, that is, the visible and ultraviolet part of the spectra, is absorbed and heats the land and oceans, longer wave, infrared energy, or heat, is re-radiated to the atmosphere. Greenhouse gases absorb this energy, allowing less heat to escape back to space and trapping it in the lower atmosphere. Over the last few centuries, due to the Industrial Revolution, and as the global population has continued to grow, atmospheric concentrations of both natural and man-made heat-trapping gases have been rising. People produce larger amounts of some greenhouse gases compared to others. Carbon dioxide is the greenhouse gas most commonly cited because human activities produce more carbon dioxide compared to any other greenhouse gas, and it's responsible for most of the warming. For example, burning fossil fuels, coal, oil and natural gas, increased combustion from vehicles and machinery with internal combustion engines, and smaller contributions from agricultural and land use changes, such as land clearing, also have significant impacts on the Earth. But how are emissions normally controlled? Trees have a natural process to remove carbon dioxide from the air, but increased cutting down of forests reduces its removal from the atmosphere, prevents heat escaping from the planet, and hinders the planet from cooling itself, and this is increasing the planet's temperature. Water vapour, which is naturally present in the atmosphere, has a strong effect on weather and climate. But as the planet gets warmer, more water evaporates from the Earth's surface to reside as water vapour in the atmosphere. This creates what is called a positive feedback loop, meaning that the more water vapour that is in the atmosphere, the more warming to the Earth's surface that will occur. In summary, human activity has interfered with the carbon cycle and artificially moved carbon from solid storage to its gaseous state, thereby increasing its concentration in the Earth's atmosphere. But the story does not end with changes we've made that affect natural greenhouse gases. Just as important is what has been happening due to man-made or synthetic greenhouse gases. When and why did synthetic greenhouse gases begin to be made and used? Our modern lifestyle has fueled the need to make and use these substances. In the late 1800s and early 1900s, refrigerators used toxic gases as refrigerants. By the 1920s, their safety started being questioned. This sparked the search for less toxic replacements. In 1928, the first chlorofluorocarbons were synthesized and considered a safe, non-toxic, non-flammable alternative to dangerous substances used then. After World War II, they were used as propellants for bug sprays, paints, hair conditioners and other healthcare products. This continued during the late 1950s and early 1960s because CFCs made air conditioning in automobiles, homes and office buildings more affordable. What are chlorofluorocarbons? CFCs are a family of chemical compounds where one element is chlorine. They're considered safe to use in most applications and are inert in the lower atmosphere. There is usually very little chlorine in the stratosphere, but with the increased use of CFCs, more is being released into the atmosphere, eventually making it to the stratosphere, where UV radiation breaks it down and releases the chlorine into the ozone layer. What's the effect of chlorine in the ozone layer? Ozone is located mostly in the stratosphere. The increasing loss of stratospheric ozone allows more harmful UVB radiation to reach the Earth's surface. Ozone absorbs much of the harmful UV radiation that causes biological damage in plants and animals. Therefore, its depletion is a major concern globally. How does ozone depletion occur? UV radiation breaks down CFCs in the stratosphere by breaking off a chlorine atom from the CFC molecule. Once free, the chlorine atom steals an oxygen atom from the ozone molecule to make a chloride monoxide. Other free oxygen atoms then steal the oxygen atom back off the chloride monoxide molecule and releases the chlorine atom, which then is free to steal more oxygen atoms from other ozone molecules. This process creates more oxygen molecules and depletes the number of ozone molecules in the stratosphere. Some of the released chlorine becomes active in destroying ozone in the stratosphere at a rate of 100,000 molecules of ozone destroyed per chlorine atom that exists. By 1985, ozone loss included the Antarctic ozone hole and ozone loss in the mid-latitudes. There was also concern because CFCs have very long atmospheric lifetimes. which limits our ability to reduce their accumulation in the atmosphere. By the 1980s, a group of synthetic greenhouse gases were recognized as depleting the ozone layer in the stratosphere, and they were called ozone depleting substances. In 1987, the Montreal Protocol was signed to reduce the production and use of ozone depleting substances by 50% before the year 2000. By 2010, nearly 97% of ozone depleting substances have been phased out. This was amended in 1990 to include phasing out various CFCs, chlorinated solvents, methyl chloroform, and carbon tetrachloride. But the chemical industry still needs substances to use in their equipment, and thus began searching for more ozone-friendly substances, those that don't deplete the ozone layer. Thus, hydrofluorocarbons were substituted for ozone-depleting substances. Today, hydrofluorocarbons are used extensively in Australia, largely in air conditioning and refrigeration, initially as ozone-friendly replacements for chlorofluorocarbons and hydrochlorofluorocarbons. Minor uses of hydrofluorocarbons in Australia are as aerosol propellants, including metered dose inhalers, as foam-blowing agents, and in fire extinguishers. Did these replacements work? The hydrofluorocarbons are emitted in smaller quantities and do not harm the ozone layer like the CFCs did. This is a good thing. However, some HFCs have high global warming potential values because they act strongly as greenhouse gases when in the atmosphere. The most common hydrofluorocarbon in Australia is HFC 134A, which has a GWP of 1,300, meaning it is 1,300 times as potent in the atmosphere as carbon dioxide. Since they tend to have longer lifetimes than CFCs, and since their use is growing rapidly, experts are becoming concerned that the increase in use means there will be more of these heat-trapping substances collecting in the atmosphere that will be difficult to remove. After all, some HFCs are up to 10,000 times more effective at trapping heat compared to CO2. Others are just so commonly used that it's their repeated use that aggravates the problem. Other synthetic greenhouse gases also have high GWP levels, though they are present in the atmosphere in smaller concentrations, and include perfluorocarbons, sulfur hexafluoride, nitrogen trifluoride, sulfuryl fluoride, and trifluoromethyl sulfur pentafluoride, which are collectively described as synthetic greenhouse gases. SGGs account for 1 to 2% of all greenhouse gas emissions in Australia. How strongly they affect things is seen by their high global warming potential values. Sulfur hexafluoride is used extensively in the electricity distribution industry, both in Australia and overseas, for dielectric insulation and current interruption in circuit breakers, switchgear and other electrical equipment, and as a cover gas in metal production such as magnesium. Sulfur hexafluoride has a GWP of 23,900. Other SGGs are even more powerful global warmers, including PFCs, which have a GWP between 6,500 and 9,200. Perfluorocarbons are a byproduct of the production of aluminium in Australia and overseas, and in addition are used overseas in the electronics industry during the manufacture of integrated circuits and plasma screens. Refrigeration represents a minor use of perfluorocarbons in Australia and overseas. There does not appear to be any significant use of nitrogen trifluoride in Australia, which is used internationally in the semiconductor production industry, initially as a replacement for perfluorocarbons. Sulfuryl fluoride use in Australia is growing rapidly as a replacement for phosphine and possibly methyl bromide in grain fumigation. It is unlikely that trifluoromethyl sulfur pentafluoride is used in Australia. Its occurrence in the atmosphere is largely as a byproduct of the production of perfluorooctane sulfonic acid, which has never been manufactured in Australia, though is a key ingredient in fabric stain repellents such as 3M's Scotchgard and firefighting foams. Rapidly growing hydrofluorocarbon emissions are seen as a significant driver of climate change over the next 50 years, and projections suggest that unmitigated hydrofluorocarbon growth could result in increased global warming potential weighted emissions. But even if a substitute is found, HFC concentrations are still expected to rise by 140% because developing countries are expected to install around 700 million air conditioners over the next decade. Over the past decades, governments and scientists have become increasingly concerned that as we continue to burn large amounts of fossil fuels and deplete our forests from doing their job, that an exaggerated greenhouse effect will occur. Most scientists agree that 2 degrees Celsius of warming above the temperature during pre-industrial time has the potential to harm all sectors of civilization. There are a few things being considered. Scientists are working hard to determine ways in which technology can be used to try to slow down or avert climate change. Scientists are searching for ways to remove carbon dioxide from the atmosphere, though they are not certain whether this will work on a big scale and if it will have any notable effect. Scientists are also considering whether injecting particles into the Earth's upper atmosphere can effectively reflect the sun's radiation back into space and thus cool the Earth. Then there is the focus on designing power plants that emit less carbon dioxide into the atmosphere. This final option requires less reliance on coal power plants and more reliance on the use of nuclear power plants or wind turbines. What suite of things has the government done? In June 2015, the government passed legislation to implement the Enhanced Renewable Energy Target Scheme so that 23.5% of Australia's electricity generation in 2020 will be from renewable sources. In December 2015, at the Conference of the Parties, a global agreement for climate action post-2020 was made. It was as part of this that Australia committed to reduce greenhouse gases by 26 to 28% below 2005 levels by 2030. This is good news because according to the Organisation for Economic Cooperation and Development, Australians are the highest greenhouse gas polluters per person in the OECD. The Ozone Protection and Synthetic Greenhouse Gas Management Act of 1989 and related acts aim to protect the environment by reducing emissions of ozone-depleting substances and synthetic greenhouse gases. The acts control the manufacture, import, export and end use of ozone-depleting substances and synthetic greenhouse gases and products containing these gases. To further reduce emissions of ozone-depleting substances, on the 5th of May 2016, the government decided on a range of measures to improve the efficiency and effectiveness of the ozone protection and synthetic greenhouse gas program. What are other countries doing about this? The US Environmental Protection Agency has proposed delisting and putting controls on a number of high GWP hydrofluorocarbons. On the other hand, the European Union also has a hydrofluorocarbon phase down in place. There are no mandated global or Australian targets to phase down Kyoto Protocol SGG emissions at present, except as contributors under post-Kyoto agreements. There are no global or Australian targets to phase down sulfuryl fluoride or trifluoromethyl sulfur pentafluoride emissions. These are important strategies because the enhanced greenhouse effect is thought by many to have caused changes in the planet's weather patterns, that is, climate change. Climate change has changed where disasters occur and has caused more frequent and more severe weather events such as hurricanes, droughts and heat waves, which result in more devastating property damage, injury and deaths. This has caused increased migration away from these regions. Climate change is believed to also be responsible for melting of the polar ice caps, which has raised sea levels. Those seas are rising very slowly and only by a very small amount. Over time, it is expected to flood low-lying coastal areas and will also contribute to increased migration away from these regions.